geometric meaning partial derivatives and gradient. And now I want to formulate theorem. If f of x, y is differentiable at x naught, y naught, then there exists a tangent plane to the graph of z equals to f of x, y at the point m naught with coordinates x naught, y naught, and f of x naught, y naught. Okay, let me denote also z naught by this value. And it has the equation z minus z naught equals to partial derivative of x with respect to x at x naught, y naught times x minus x naught plus partial derivative of f with respect to y in the same point times y minus y naught. So analogously to derivative for one variable, where derivative is connected with tangent line, here for functions of two variables you see partial derivatives are connected with tangent plane. So proof. For the proof, let me recall that we had several possible understandings of tangent plane, and now I want to use the following. So we consider the graph of our function. So here is, that is x naught, y naught, that is our point m naught, and one of possible understanding was as follows. So every plane has a normal, a vector which is orthogonal to that plane, orthogonal, and this it allows to define tangent plane as such a position of the vector n that it should be orthogonal in limit to arbitrary chord. So we draw arbitrary chord, arbitrary interval which connects two points of our graph, and in the limit as m tends to m naught, this limit position should be orthogonal to n. So let me write it down. the normal to the tangent plane is characterized by the following property. The following property. The normal n. Normal n. N is orthogonal to the limit position of an arbitrary chord m naught m, which connects points of the graph points m naught and m of the graph z equals to f of xy. So the limit position is m tends to m naught. So that is I tried to draw on the picture here. We have m on the graph. M naught is a fixed point, so m tends to m naught, and limit position of our chord should be orthogonal to the normal vector. Okay, so f is differentiable at x naught, y naught. Hence, we can write the following representation. F of xy equals to f of x naught, y naught plus differential of f at the point x naught, y naught plus little o of the vector, okay, I'll write here dx dy, where, okay, s, better to say s, this length tends to 0, where dx is x minus x naught, dy equals to y minus y naught. That is the definition of differentiability. So, if we remember z equals to f of xy, z naught equals to f of x naught, y naught, then I can rewrite it as follows. Z minus z naught equals to, now let me write down the differential. The differential is equal to partial derivative with respect to x at this point times dx, and dx is x minus x naught, plus partial derivative of f with respect to y times y minus y naught. That is the first differential, plus little o of, okay, let me write x minus x naught, y minus y naught. So I substitute dx and dy. Okay, now consider the part of this definition without little o. So forget about this little o and write down what remains. That is this equality. So what I do now, I look at the definition, then I forget about this little o part, and I consider what remains. And if we look at this equality, then we can recognize here that is an equation of a plane with normal vector and what are the coordinates. So let me recall that in general, from analytic geometry, if we have general equation of a plane is like that, then A, B, C are coordinates of the normal vector, not normalized. I mean, I don't care about norm of this vector. I know that usually n denotes normalized vector, so with norm equals to 1. Here it in general need not to be of the unit norm. Okay, what are coordinates? So if I put z minus z naught to the right hand side, then coefficients in x we have this one. So that is the first coordinate, df over dx at x naught, y naught. The second coefficient in y is partial derivative of f with respect to y. Third coordinate, coefficient in z, when we put it in one side, like here, we obtain -1. So, what is written here is precisely an equation of a plane. Normal vector looks like that. Now, what is about coordinates of this vector m naught m? M naught m. So m has coordinates, okay, arbitrary point of our graph, x, y, and z, which is like that. So, coordinates of m naught are written here. It means that m naught m has coordinates x minus x naught, y minus y naught, z minus z naught. Better to say here f of x y minus f of x naught y naught. That is the vector from m naught to m. Remember, m is a point of our graph, with such coordinates x, y, and f of x, y. F of x, y. Okay. Now, what is about cosine of the angle. So cosine of the angle phi. Phi is the angle between n and m naught m. Okay, that is phi. Here is angle phi. That is the angle phi between n and m naught m. So cosine phi can be written as scalar product n times m naught m divided by product of lengths. That is a formula from analytic geometry. Cosine of the angle between two vectors. Now let me write it down. So what is it? That is n is written here, m naught m is written over there. So what we have, partial derivative f with respect to x at x naught y naught times x minus x naught plus partial derivative f with respect to y x naught y naught times y minus y naught. So I consider scalar product. That is sum of products of corresponding coordinates. Minus 1 times the difference between f of x y minus f of x naught y naught. That is what written in the numerator, and then divided by length of n, square root of partial derivative of f with respect to x squared plus partial derivative of f with respect to y squared plus 1. And here I should write the length of f naught m, that is x minus x naught squared plus y minus y naught squared plus f of x y minus f of x naught y naught squared. That is this cosine. Okay, I want to prove that this angle phi tends to 0, tends to pi over 2, sorry. We want to prove that n is orthogonal to the limit position. If angle tends to pi over 2, then cosine phi tends to 0. So it means that I want to prove that this cosine in modulus tends to 0. So I should estimate it somehow to show that it tends to 0. Okay, what is it? I'll start with denominator. For denominator, so to get an estimate above, I should estimate the denominator below. The first term, forget about first two terms, I'll estimate by 1. The second, here I'll forget about the last term. So square root of x minus x naught squared plus y minus y naught squared. And for the numerator, look at the definition of differentiation. What is written here? Z minus z naught. Z is precisely f of x y. So you see f of x y minus this. Here it is written. So what is written in numerator is the difference between this and that. So according to the definition of differentiability, this is little o of this norm, x minus x naught, y minus y naught model. And now, what is the meaning of this little o? In fact, little o means that when we divide this little o to this quantity, this ratio tends to 0. But what is this norm? It's precisely that one. Length of this vector is written here. So this quantity tends to 0 as m tends to m naught, as it should be according to our understanding of the tangent plane. So if we understand the tangent plane in this way, then we obtain immediately from the definition that the tangent plane exists and it has this equation. So theorem is proved. Okay. Now let us consider the gradient, and for that reason I need firstly to consider so-called directional derivative. So directional derivative of a function f of x along a vector v is the limit, if it exists, of course, the following limit as t tends to plus naught, that is one-sided limit, or the following difference. So I forget to indicate which point is the limit of a function along a vector. I forget to indicate, so we should insert here at the point x naught. That should be here. So directional derivative of a function f of x along a vector v at the point x naught is the limit, if it exists, f of x naught plus t times v minus f of x naught over t. Let us think what is the meaning of this definition. So it means that if we, let me draw the picture here. So we have a point x naught, we have a vector v. So what means directional derivative? It means that we consider such a function x naught plus tv and take the derivative of our function f. So let me recall that what is written here is derivative of function of one variable t. So in numerator we have increment of that function of one variable, And it means that what is written here is instantaneous rate of change of the function of one variable f of x naught plus t times v. So phi of t, let's say, right? And in other words, it means that what we do, we consider the rate of change of our function f at the point x naught in the direction of the vector v. Instantaneous rate. So instantaneous rate of change in one direction. We have a point x naught and we consider only that direction. So for functions of two variables, for example, if we are here, then we go in a direction on the plane and we consider only the rate of change of our function in that direction. Now we can understand easily what is this directional limit. So let me formulate it as a theorem. 2. If f is differentiable at x naught, then f has directional derivative at x naught along arbitrary vector v, which is equal to, oh, by the way, I forget to introduce notation. So the notation is as follows: df over dv at x naught, by definition, is equal to, so directional derivative at x naught equals to scalar product of gradient f at the point x naught times vector v. Proof. Once again, let me write down what is our definition of differentiability gives. So we know that according to the general definition, it can be written as gradient times the increment of our argument. It's like that, yeah, plus little o of this vector x naught plus tv minus x naught. So I wrote general definition. Here it is written for two variables, but now here it is written for arbitrary number of variables. By the way, I didn't indicate. I didn't indicate that vectors and points are in Rn. So let me indicate it here in Rn. In Rn. Yeah, so here also in Rn. Rn. In Rn. So here I wrote the definition of differentiability. In general, we have here arbitrary vector x. So x minus x naught. Here also x minus x naught. Instead of x, I substitute that one. Now, what is that? Here, that is equal to t times norm of v. Recall, t is positive. T is positive. T tends to plus 0. Norm of v is fixed. Of course, it in general, the definition also, you see, if v equals to 0, then it's a little bit stupid. If v equals to 0, then we have 0, and automatically it's 0, right? And of course, the formula also holds for v equals to 0. 0 equals to 0. And in fact, you don't need to suppose that f is differentiable to get it. So if v equals to 0, then this equality is trivial and the assertion is trivial. And if v is not equal to 0, then I can forget. So little o of t norm v equals to little o of t, as t tends to plus 0, right? Plus 0. Okay. Then here I can cancel x naught. And what remains? So let me rewrite now. F of x naught plus tv minus f of x naught equals to t times gradient f of x naught times v plus little o of t. If I divide this equality by t, then we obtain, so the right hand side has this limit because little o of t divided by t tends to 0. Hence the left hand side divided by t, it's here, also has a limit which is equal to this scalar product, and it gives the equality which we wanted to prove. So that is, the proof is over. Now, okay, let me draw it here. Geometric, next theorem. Oh, maybe a few words about definitions. You know, sometimes you can find in some textbooks the definition of directional derivative in slightly different manner. So sometimes this number is added to the definition. I don't want to do it. So without that, and of course, two versions of the definition of directional limit, of directional derivative, coincide for vectors v of the unit length. And that is in fact most important case, of course. Now I can formulate theorem 3. Geometric meaning of the gradient. If f is differentiable at x naught in Rn, then the maximum of all possible values of directional derivatives df over dv at x naught for v of the length 1 is attained for v equals to gradient f divided by the length of this gradient. Of course, I should suppose also the gradient is not 0, otherwise makes no sense. And the minimum of the same quantities is attained for v equals to minus gradient f at x naught over gradient f at x naught. Or I can write df over dv at x naught less or equal than, so gradient, length of gradient greater to equal minus length of gradient okay. Now so I don't like how I formulated it, because yeah, of course makes no sense to write something which can be 0. So I should add here, if f is differentiable and gradient f at x naught is not 0, right? That is, otherwise makes no sense, but Let me also write down the remark. The inequality star, let's say, right? Inequality star holds also for gradient f at x naught equals to 0, right? So inequality can be considered without this restriction, but it makes no sense to write down such a ratio if this is 0, right? That is not good. Okay. So, proof. Proof is very easy. So I refer to theorem 2. Implies that the partial derivative, directional derivative is equal to the product, scalar product of gradient times v. We know that the scalar product can be estimated by Cauchy, Bunyakovsky-Schwarz, inequality, like length of gradient times length of v. Length of v equals to 1 by our choice of v. Hence, you see that maximal we have the right hand side of star, and of course the left hand side also follows from the same inequality if we consider this with minus sign. And what remains when we have equality? Inequality in Cauchy-Bunyakovsky-Schwarz takes place, so equality here, if and only if gradient is equal to a constant times v. And since, in fact, I can put here also modulus without any problem. So equality if and only if gradient f equals to cv. Hence, we obtain, since vector v has length 1, v equals to plus or minus gradient over the length of this gradient. And these are only two cases when we have equality here. And you see, if we choose v equals to plus, then we have plus here, maximum. If we choose minus, then we have minus here, so minimum of the values of our directional derivative. So theorem is proved. And why this is geometric meaning of the gradient? Because remember, what is directional derivative? Directional derivative indicates instantaneous rate of change in the direction. So we have many directions. Our function is defined somewhere in the neighborhood of our point x0, and so here is the graph of our function, and you see when we move in a direction, then values change somehow, right? Change somehow. So in different directions, we obtain different changes of our function, right? And the maximal rate is precisely when we move in the direction of gradient. It explains why gradient is so important for the questions of the search of extrema. So it's natural to expect when you move in the direction of the maximal rate of change, then you approach to the maximum. Of course, in general, that is not true, but it works quite often for rather simple cases. Okay, then this section is over, and now section 3, partial derivatives and differentials of higher orders. Okay, let me erase for a while. So when we considered usual derivatives of functions of one variable, how we defined, for example, the second derivative. So what is the second derivative of a function of two variables? What we need to do? We need to consider the first derivative as a new function, and then to take the derivative of that new function. So for functions of one variable, what we have, recall, if y equals to f of x, then y double prime is by definition derivative of the first derivative, right? So we take one derivative and then we take second derivative. Now we have no derivatives at all. Instead we had partial derivatives, and also we had some replacement of another notion from one-dimensional calculus, namely we replaced differentials. So let's start with partial derivatives. So definition. If partial derivative the partial derivative df over dx I, let's say, at x is defined in a neighborhood of x naught, then we consider it as a new function. Hence, then we can define partial derivative with respect to another variable, maybe the same, of that first derivative at x naught. So what is it? I can write it in usual way, like, oh, maybe it's very huge formula. I don't want to write it down just now. So we know how to define partial derivative, and that is, by definition, notation is as follows: partial derivative of f with respect to x j x I. Or also sometimes it is denoted as xi xj. Change the order here. So firstly you differentiate with respect to xi, then with respect to xj. And yeah. So you see, x, the function is the function of n variables. So x is x naught in Rn, and ij from 1 up to n, any number of variable is allowed here. So, and you see that in general we can define partial derivatives with respect to two different variables in a different order, and sometimes the order is important. So I'll start with an example. Consider such a function of two variables, f of xy equals to xy times x squared minus y squared, x squared plus y squared if x squared plus y squared is not 0, and 0 for x squared plus y squared equals to 0. That is our function. So let me consider what are partial derivatives of the first order. So df over dx. What is it? If we are not at the origin, then the derivative can be defined directly. So we differentiate with respect to x. It means y times x squared minus y squared over x squared plus y squared plus xy times derivative of the ratio, that is 2x times x squared plus y squared minus 2x times x squared minus y squared over x squared plus y squared squared. Or what is it? So 2x cubed is cancelled here, 2xy squared is multiplied Okay, how to write it shorter? Okay, let me write like that. Y times x squared minus y squared over x squared plus y squared plus we have 4 2x cubed is cancelled, 2x, 4x squared, y cube over x squared plus y squared squared for x squared plus y squared not equals to 0. And if x squared plus y squared equals to 0, then we proceed by definition, that is limit as delta x tends to 0, f of delta x 0 minus f of 0 0 over delta x. And if we substitute, we obtain y is 0, then that is 0, so numerator is 0, that is 0 if x squared plus y squared equals to 0. That is partial derivative with respect to x. Analogously, we can compute partial derivative with respect to y. Okay, here at a point xy, also at a point xy. Once again, we have two possibilities. So if x squared plus y squared not equals to 0, then we obtain x squared minus y squared over x squared plus y squared plus xy. So derivative of numerator gives minus 2y x squared plus y squared minus numerator times derivative of denominator x squared plus y squared squared, that is x times x squared minus y squared over x squared plus y squared, and minus 2y x squared is preserved, y cube is cancelled, so minus 4 x cube y squared over x squared plus y squared squared, as x squared plus y squared is not 0, and once again 0 if x squared plus y squared is 0. Yeah. Partial derivative of the first order are computed, and then we can compute partial derivative of the second order. So I'll start with partial derivative d2f over dy dx. So I take this partial derivative, and so by definition, that is limit as delta y tends to 0, partial derivative of f with respect to x 0 delta y minus partial derivative of f with respect to x at 0 0 over delta y. So that is 0 0 here. And if I substitute instead of x 0, then second term here is 0, x is 0, delta y, so I have here x is 0 minus 1 minus delta y, that is limit delta y tends to 0 minus delta y over delta y minus 1. Analogously, d2f over dx dy at 0, 0 is equal to the limit as delta x tends to 0, partial derivative of f with respect to y at delta x 0 without partial derivative with respect to y at 0, 0 over delta x. So here I should substitute y equals to 0. It gives only delta x, that is limit as delta x tends to 0, delta x over delta x, and that is 1. And they are not equal. They are not equal. So, in general, partial derivatives with respect to, these are called also mixed partial derivatives. Is it f or just if this is question about that one, so sometimes f double prime also is written, but also it can be written without this double prime. It doesn't matter. So both possibilities are accepted. You can put here double prime, it's no problem, but I prefer to write without it. Okay, so then okay, now very important result. Theorem 1 of this section is, which says when we can forget about this possibility and mixed partial derivative, such derivative, they are mixed partial derivatives. That is, to distinguish with such partial derivatives like that. That is not mixed. Mixed are those ones, when we have different variables. Mixed. So, theorem 1, that is independence of mixed partial derivatives of the order of differentiation. Differentiation. If partial derivatives okay, once again, the partial derivatives d2f with respect to dx dy and d2f with respect to dy dx exist in a neighborhood of x naught y naught and are continuous at x naught y naught, then they are equal. They are equal at x naught y naught. So partial derivative of second order with respect to xy at x naught y naught, and in in first order, they are equal. So it's like sufficient condition for differentiability. Remember that if partial derivatives of the first order are continuous at a point, then the function is differentiable. Here we have a generalization for the second order. So, proof. Consider such an expression, a function better to say, capital Phi of h equals to f at x naught plus h, y naught plus h, minus f at x naught, y naught plus h, minus f x naught plus h, y naught plus f at x naught, y naught. This expression we'll consider, in fact, twice to understand why we have such an equality. Okay. Firstly, we note that phi of h is the increment of the function which function, okay, let me write f of x y naught plus h minus f of x y naught of the variable x. And let me denote this function. Let it be, let's say, phi of little phi of x. What kind of the increment? Namely, so phi, capital Phi of h equals to little phi of x naught plus h minus little phi of x naught. Why? Just substitute. So, look. Phi of x naught plus h. What is it? I substitute instead of x, x naught plus h. That one minus that one. So, you see, this corresponds to phi of x naught plus h. Precisely this difference. And twice underlined is that one. With minus, you see. Minus, we have minus, 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 plus. Okay, then look what is written here. So we know that there exists so both partial derivatives of the second order exist in a neighborhood, and it means, according to the definition of partial derivative of second order, that what is inside also exists in a neighborhood. So partial derivative with respect to one variable doesn't matter with respect to both x or y, exists also in a neighborhood. So look, what is about derivative of phi? Phi is a function of one variable. If we differentiate it with respect to x, it means we differentiate f with respect to x here and here. And if this partial derivative exists, then partial derivative with respect to x also exists. So phi is differentiable. Phi is differentiable. Hence, by Lagrange mean value theorem, Lagrange mean value, there exists a point psi such that we can write here such a difference phi prime at xi times x naught plus h minus x naught, and that is precisely phi prime of xi times h. And what is phi prime of xi? We differentiate. That is partial derivative of f with respect to x at which point? So instead of x I substitute xi, and then y naught plus h, minus partial derivative of f with respect to x, the same xi, but now y naught times h. That is equal to okay, I write here now. Once again, I apply Lagrange mean value theorem. But now we have difference, so xi is fixed. One variable is fixed. Second variable varies. So it means that we have now second derivative of f with respect to y of the first derivative, and here we have psi eta times y naught plus h minus y naught times h. So once again, let me show what I did. We had difference between partial derivative with respect to x, where the first coordinate is the same, it is equal to xi. Second coordinate varies. So we have derivative of the function df over dx of xi y with respect to y, and it gives that one. So that is partial derivative of f with respect to y and then with respect to x, psi eta times h squared. Recall that was phi of h. Now consider phi of h as the increment of now another function, f of x naught plus h y minus f of x naught y, which is, let it be now, psi of y. So it means I represent phi of h as psi y naught plus h minus psi at y naught. So I will not do it in details. We once again substitute firstly, instead of y, we substitute y naught plus h, and then y naught. And after that, once again apply Lagrange mean value theorem. Lagrange mean value. Then we have a point, let it be e to 1 another, times h. Psi prime is precisely partial derivative of f with respect to y, x naught plus h e to 1 minus partial derivative f with respect to y at x naught e to 1 times h. Once again we apply Lagrange mean value theorem. Lagrange mean value. We obtain now second derivative of dx dy at psi 1 e to 1 times h squared. So we have such a equality. As a result, d2f over dy dx at psi eta times h squared equals to d2f over dx dy at psi 1 e to 1 times h squared. Of course, I can forget about h squared. And then remember where are psi, psi 1 and so on. Psi 1 are between x naught and x naught plus h. Eta e to 1 are between y naught and y naught plus h. Of course, also they depend somehow, you see, for example, here eta depends on psi, and here vice versa, psi 1 depends on e to 1, but it doesn't matter. Why? Because if h tends to 0, hence both points psi eta tend to x naught y naught, and psi 1 e to 1 tends to x naught y naught. So because if h tends to 0, e to 1 eta between them so tend to y naught, and angularly for psi. So hence if we send h to 0, and remember I cancelled h squared first, that's important. I have equality for arbitrary sufficiently small h. I forget about h squared then. And after that, I take the limit as h tends to 0. So points tend to x naught, y naught, and we have, as a result, the relation which I wanted to prove. Partial derivative is the same in both orders. And that's all. Thanks for your attention.